Hello, and welcome to our presentation this afternoon on Monash's Woodside and Chacellery building. It's great to be back at the South Pacific Passive House Conference, although in this virtual format. Monash has been talking about its buildings and its plans for passive house buildings for many years now, and I'm really pleased this afternoon to be able to introduce the speakers who will take you through these two buildings, as much as anything because it's a transition from me just talking to you about what we'd like to do to the reality that these professionals, these builders, these designers, these wonderful, inspired people have done what we've been talking about for all these years, and these buildings are now real and valuable assets to the university. So just a quick recap on that journey. So Monash started out back in around 2014 with our test and learn. We had a retrofit project that we worked through the passive house planning package to create a great outcome for the building. By no means do we hit passive house on this building, but we really got the performance. We got the takeaways of what it means to be in a passive house building. It's the office building that I've been working in ever since, and it's a really great outcome for the occupants. The energy performance has also demonstrated great returns in what we were expected to do. In the interim, we took on the biomedical learning and teaching building featured here. It was a step from what we'd been building towards passive house. We couldn't go all the way because we felt the industry wasn't quite ready and the politics within Monash wasn't quite ready to take the full leap, but it allowed us to demonstrate that the principles could be applied into construction and that air tightness wasn't such a scary thing at scale. It allowed us to hit our first passive house certification, which was the Gillies Hall, a beautiful building with timber as its primary structure form, lovely to be in, great indoor environment quality, now verified through our researchers as better than the existing residences that we have on campus, using around half as much energy as those other residences that we have, and with its rooftop solar and our wind farm that's up in Murrawarra through the power purchase agreement, is now operating as a 100% renewable powered building. So that brings us to our new buildings. The Chacellery buildings, which you'll hear about first, from ARM and Oricon, is a wonderful new, effectively seat of power for the university. This is where our executives reside. The people who make the decisions about how to build and how to shape the campuses are now living and breathing in a building that was designed and constructed to the passive house standards. For various reasons, we came up a little bit short on this building, but still the outcome is there. And then finally, the Woodside building, which is at scale, a full-on education office building that really demonstrates that, for me, Australia has arrived in the passive house space. We started with the wonderful residences building, we've built multi-resi now, we've built office buildings, and now we're building this bespoke education facility that really represents that you can build passive house of any nature in this country using any structural system. We've shown that you can build with timber, we've shown you can build with concrete and with steel. So for me, the takeaways from this journey and what I'm passing on to the executive and anyone who cares to listen is that passive house gives you that integrated design framework. It forces the teams to come together in a wonderful way to design a great outcome. And then it gives you that quality assurance in the construction that means that you get what has been designed on paper. The buildings reflect the performance and deliver the performance that you set out to achieve. These are wonderful buildings for our occupants, and they have allowed us on this renewable energy path. So we're very excited to hear from the speakers today, and hopefully you'll take away lots of inspiration that you can apply onto your projects into the future. Thank you very much and enjoy the rest of the presentation.
Thanks, Rob. My name is Jeremy Stewart and I was the design architect for the project. Rather than go through a series of construction details and numbers about how the building performs, I'll give a brief outline of the design and how we incorporated passive house principles from the outset of the project. This approach led to what we think is an exciting building that seamlessly incorporates passive house. For those who don't know, a Chacellery is basically an administrative or office building. In this project, we are also able to provide a series of public spaces at ground level for use by the wider campus. The architectural brief was to produce a building that is secure but welcoming, functional but engaging. The building was to read as a quiet icon. At the very beginning of the design process, we undertook an analysis of the precinct to see where we could build. This diagram describes the public open spaces, the pedestrian pathways and entry points into the precinct, along with the main access routes to the south and the east. The precinct analysis was then transformed into a 3D massing model. As you can see, the Chancellary will eventually have built form to the north and the east. The building will have frontages to the Forum to the south and to the Religious Centre to the west. In conjunction with the siting analysis, we also undertook an analysis of the built form implications. Here you can see some of the forms we reviewed. The long question mark was rejected as the facade volume ratio and travel distances were too high. The long thin building placed a high heat load on one side of the building, so it was also rejected. The courtyard form worked well from the perspective of the facade volume ratio and for daylighting, but given the size of the floor plates we were looking at, the courtyard would have been almost unusable, so this was also rejected. In the end, we settled on a U-shaped plan with an enclosed void. This had a good facade volume ratio and maximised light penetration into the centre of the building. Whilst we were working on the siting and massing studies, we were also investigating the architectural concept. The building is conceived of as a contemporary town hall, a civic building that accommodates management and the public. To facilitate this, we introduced a public colonnade or stoa that you can see in green in this image. This had the added advantage of providing some shelter from the icy winds which come from the south. This was complemented at ground level by generous public spaces which were available for the wider campus. We then located the administrative and executive areas to the upper levels. In section, you can see how the key elements came together. The colonnade is on the left, supplemented by the public areas to ground. The formed plywood atrium rises up through the building, providing light and a central focus for the administrative and executive areas located on the upper levels. You can also see the double facade that wraps around these levels. Here we have the obligatory airtight and thermal envelope drawing. As you can see, we excluded the basement from this envelope. You can also see where we notched the envelope around a series of grottos located on the western facade. This allowed us to simplify the detailing around the grottos, much to the relief of the builder. You can also see the double layer skin to the upper levels. This consists of a folded steel screen which is offset from a rationalised high performance inner facade. I'll now quickly run through the various levels of the building, starting at ground. This is the public level of the building. You can see the main entry highlighted in blue at the bottom left, with a function room for 100 people located immediately above it. This room is accessed via the main central atrium, with a large engagement or display space located to the bottom left. This has direct access from the colonnade. At the top right corner, you can see the alumni lounge area. All of the service areas and the core are located along the western facade on the left-hand side. This allowed us to eliminate any glazing facing westwards at this level and thus reduce the heat load. You can also see the series of grottos I mentioned previously, which have been arrayed along the facade to attract people up to what would have otherwise been a blank facade. As the university already has a large production kitchen on site, the decision was made to only provide a plating kitchen, thus reducing the electrical load. Here we have a view looking up through the atrium with the formed stack plywood balustrade. You can also see that the lower levels of the plywood have been spaced to capture noise at this level and prevent it travelling up the building. The large Margaret Preston image to the atrium ceiling is printed onto acoustic material to further dampen noise within the space. To the right we have the engagement space at the top and the alumni lounge on the bottom. Moving on to level 1. All of the office levels are laid out on a 1.8 metre grid and incorporate access floors to allow for changes in the future. The building grids are 9 metre to the side and an 11 metre grid at the atrium. This provides an overall plate depth of 18 metres to each side of the atrium, which is ideal from a daylighting perspective. All of the meeting spaces are located inboard. We provided a wide range of spaces throughout the administration levels, ranging from informal lounge areas to large meeting rooms. The highlighted stair acts as a vertical pathway through the upper levels. To encourage use, it's been oversized and glazed. At the southern edge of the atrium, you can see a T-point which overlooks the forum. This element occurs throughout the admin levels and was designed to encourage staff to linger and interact with each other, something that was lacking in the old Chancellary building. Here you can see the view from level 1 through the atrium to the north. On the left we have the T-point. As you can see, the facade screen has been designed to allow for views through to the wider campus. On level 2 we replicated the layout at level 1 but introduced a 34-person meeting room to the northwest corner and a generous acoustically isolated social space to the northeast. The social space was located at this level to provide easy access via the adjacent stair. Hopefully this is discouraging people from using the lifts. Here we have a shot of the social space to the top left and the connecting stair. Throughout the project, we have incorporated elements from Monash's history. In the social space, we've integrated images from the foundation of the campus into the wallpaper, while the stair utilises elements from the original Chacellery building. In the late 60s, student protesters occupied the Chacellery building. As the building was lacking in public spaces, they resorted to gathering on the main stair. Given this rich history, we attempted to salvage the stair. Unfortunately, we were not able to retain all of the elements, but we have replicated the profile of the original treads and the balustrade. The upper level consists of the executive. The original Chancellery consisted of a set of self-contained offices that didn't encourage interaction between staff. Given the nature of the work undertaken on this level, offices are still required, but we've broken the space up into 6 suites which share meeting rooms and facilities. A larger Vice-Chancellor suite and waiting area is located at the southwest corner of the floor plate. As per all levels, a communal tea point is located to the south of the atrium. And a view from the said tea point on the executive level. You can see how the clerestory glazing provides light to the entire perimeter of the atrium, which filters down through to the levels below. The overall dimensions of the Margaret Preston image is 30 metres by 11 metres. Given the original image is approximately 30 centimetres square, it's a pretty impressive piece of scaling. I'll now quickly run through the facade system. As previously mentioned, it consists of a double layer system, an internal waterproof high performance facade, and an external screen that acts to minimise heat loads and to control light. Architecturally, the outer screen references the foundation of the campus and its technological focus and mid-century modern architecture, but via a contemporary interpretation. Architecturally, the inner skin was conceived of as a background for the screen. The intent was for it to be flat, simple and easy to construct. There were numerous discussions about where the insulation should sit, what the wall build-up should be, what various U values were required and what it should be constructed from. As the project was based on a design and construct contract, at tender we drew a system that met the passive house requirements, and during construction we worked with Kane to develop the system that they were confident would meet the various design parameters. This system worked well as it ensured that everyone was confident that we would get the best outcome. On the construction shot to the left, note the outriggers at the top that support the screen. Here we have a render of the southern facade with the screen. The screen wraps around the building at the upper levels and consists of 2 main panel types, a simple chevron panel and a complex folded panel. The southern facade consists solely of folded panels, while the northern facade consists of chevron panels. The east and west transition between the two forms. By varying the width of the folded panels, we were able to produce zones of compression across the facade. A render of the western facade. You can see the 2 panel types here, the chevron on the left and the folded form on the right. You can also see one of the compressed zones that I mentioned. The panels started as complex twisted manifold forms that were then rationalised into folded panels. These were all designed to be cut from a standard sheet size in order to minimise waste. As I mentioned earlier, we spent quite a lot of time working to minimise the number of facade penetrations. In order to achieve this, we developed a system where the panels were attached to a series of ladders, which were then attached to the slab edges via the outriggers I pointed out earlier. Early on in the design process, the outriggers occurred at 3 points on each ladder, but we managed to reduce this to 2 points. This significantly reduced the number of facade penetrations. This approach also allowed us to create the irregular outer screen without impacting the performance of the facade beyond. A shot of the screen under construction. It was fabricated by a local company, Fab Metal, who did a fantastic job. You can see Gordon and Jack down in the bottom left corner there to give you an idea of the scale. Here we have a shot of the western facade with the grottos. A close-up of the grottos. You can see how these have allowed us to create an interesting and welcoming facade. Well, we think it's interesting, on what would have otherwise have been a very blank facade. The northern facade at the end of the atrium on the left. We compressed the chevron panels here to address the additional heat load given the full height glazing. To the right, a view of the building from the northwest. The eastern facade with the colonnade. This is the main ceremonial entry to the building. You can see one of the artist columns here that make up the colonnade, in this case a column by René So. And finally the southern facade with more of the artist columns to the colonnade. The VP one's a personal favourite. There are 7 in total with the ability to introduce more at a later date. That's me done. I'll now hand you over to Kia.
Thank you, Jeremy. Hi everyone, my name is Kia Mahmoudian and I'm going to share with you some of the building services and ESD details, challenges and lessons learned during the design and construction of Monash Chacellery building. Oregon has been on the journey with Monash University to move toward their ambitious net zero emission target by 2030. Some example of Monash net zero emission initiatives includes building world-class high-performance buildings, all-electric buildings, eliminating reliance on fossil fuels, on-site generation and management of renewable energies, and being exemplars in energy sustainability in Australia. In order to bring new Chacellery building to life, and considering stringent passive house energy budget, we needed to understand and follow the passive house principles closely and apply them to the project in a right manner. These being passive solar strategy, high performance thermal envelope, air tightness, high efficiency HVAC and components, and thermal bridging free construction. The first step was to make the most of passive measures to minimize surrounding environment impacts on the building. This would not be possible without collaboration with the architect and facade consultants. High-performance thermal envelope was the key to energy performance and the thermal comfort of the occupants in the building. Proposed building shading elements were quite complex, and dynamic simulation of the shading was difficult and time-consuming, but it was necessary to ensure performance of the building is met. While we were working on optimizing thermal envelope, we also needed to select a right HVAC system for the building. Given limited energy budget, we conducted extensive energy simulation for different type of HVAC systems and different facade scenarios, window to wall ratios, and glazing performances. Obviously, air tightness and thermal bridging were also very important element of the design, which required a lot of detailing and interdisciplinary coordination between the facade, ESD team, and the architects. Being a cooling dominant office building, we had to manage internal loads. Therefore, we reviewed energy consumption of all the internal loads, such as light fittings, computers, screens, appliances, in order to verify realistic internal loads rather than using rule of thumb or generic assumptions. Dynamic energy simulation helped us with finding the most suitable HVAC system for the building from both energy efficiency and thermal comfort point of view. We did a market research to find suitable HVAC components with proven track records and testing evidences. This was challenging as most of the passive house certified products were either not available in Australia at the scale that we needed for this project, or were also pretty expensive, being mostly made in Europe. We looked at many different systems like VRF system, conventional VAV, underfloor air distribution, fan coil units, and active and passive chill beams in order to find most suitable system for this building. For us, thermal comfort of occupants was as important as energy efficiency. Having high performance thermal envelope gave us more confidence about thermal comfort of occupants. So we needed to make sure HVAC system is going to provide great level of comfort, and we performed extensive thermal comfort modeling for different HVAC systems to ensure our HVAC system would also tick all the boxes. The next important step for HVAC system design was to find opportunities to further improve HVAC system energy efficiencies. We looked into HVAC system components and how we can improve our design. Our simulation suggested that after compressors and heat rejection systems, fans and pumps are the biggest energy consumer of the HVAC system. So we adopted a new strategy to reduce pressure drops across piping and ductwork network in the building. Main HVAC and building services design principles that we applied to this project were using of chilled water and heating hot water fan coil units with direct outside air system, incorporating heat recovery units with minimum efficiency of 75%. We included active humidity control in high occupancy areas, all electric high efficiency 4-pipe heat pump system used with integrated heat recovery system. You would expect COP ranging between 3 to 7.7. Optimizing pipe work and duct work was to minimize the pressure drops, and system losses were the key point in the design. We also adopted modular air conditioning system design for each space to make sure that air conditioning is provided when it's needed and it can be deactivated when not in use. Having more confidence on the building operation and less unknown in our design, we avoided using any unnecessary safety factors, so our systems are appropriately sized for the building. We trace all losses and gains, for example, in domestic hot water system or a cold water system, and we provided with extra insulation to the stormwater to minimize any heat transfers that unnecessary in the building. Heat pump system were also used for domestic hot water generation, and from electrical perspective, high efficiency light fittings were used, and some features like daylight harvesting, occupancy sensing were incorporated into our design. Besides our focus on design element of the project, early industry engagement was critical and necessary. So we arranged series of workshops, not only to learn from professionals that's already working in a space of passive house and construction of the passive house buildings, but also to get the building construction industry on board with the passive house project of this scale, which was soon going to market for pricing and tendering. Here are some of the tips and lessons learned that I would like to share with you and finish my presentation off today. First of all, avoid using a stupid engineering rule of thumbs. This would save your client a lot of money. Stick to the facts and the building physics principles. Remember that one size doesn't fit all. You need tailor-made solutions for your particular projects. Trace system inefficiencies and losses. You will find a lot of opportunities to improve your design and manage your building energy losses. Also remember, the building must look great and feel great. So thermal comfort is as important as building aesthetic and also as important as energy efficiency. And remember, you need to make sure you have a high performing building envelope in order to achieve good thermal comfort. Thermal comfort is a shared responsibility. It's not just HVAC designer's responsibility. Collaborating with project team is the key to successful delivery of passive house project. So take everyone's on the journey with you. This is the end of my presentation today, and now I hand you over to Jack from Kane Construction. Thank you very much.
Hi everyone, I'm Jack, and I was the design manager from Kane who worked with the team, including Jeremy and Kia, on delivering the new Monash Chacellery building. A quick background on the project from a Kane perspective. So we were awarded the project at 80% under a D&C contract in late 2018, and the project was completed and handed over to the university in late 2019, with occupants moving in early this year, just before COVID-19 hit. The project was designed originally as a passive house project, as you would have just heard, but during tender the decision was made to remove the certification requirements and drop the performance values. And so in the end, it was, I suppose, a high performance building rather than a passive house certified building. I'm quickly going to touch on a few points from the head contractor perspective, including construction detailing, trade packaging and de-risking from a head contractor perspective. Some comments on cost and an unexpected issue that we found towards the end of the project, and then some final thoughts on passive house after working on my first ever passive house project. From a design manager, head contractor point of view. So first up, construction detailing around walls and air tightness. So I'm sure I'm preaching to the converted on this one in this forum, but obviously wall detailing is super important and quite complex on these projects from a business as usual perspective. So you can see in the image on the top right, the standard wall detail drawings, which are showing the blockwork arrangements, which is a fairly typical, blockwork is on most projects now. However, with passive house requirements and trade input and the air tightness lines, you can see that the wall build-ups for even standard blockwork become quite significant. And I think one of the things that Kane really introduced from our perspective was having the air tightness lines moved away from the finished wall surfaces. So we were quite concerned with having trades finishing and fitting off on finished walls that were fully closed up and penetrating our air tightness line. So as you can see in the image on the left, wherever possible, our air tightness line sat within a cavity that was pretty much inaccessible from finishers' trades to protect it from being inadvertently damaged late in the piece. And then as you can see in the image in the middle, wherever possible we had tape going crazy, probably more so than necessary possibly, but I guess from a risk mitigation perspective we were more comfortable doing all fixings being taped than worrying about there being fixings that had been missed later and were unable to be fixed and addressed. The next thing is construction detailing around walls with the insulation and thermal breaks. So in the image on the left, you can see a fairly standard setup of a precast lift core with a blockwork wall coming into it, which was in a basement. It had been documented with the blockwork coming right into the precast, which is fairly standard, and our trade would have just gone ahead and done that. And then at the last minute on site, we realised that that was going to be a thermal bridge, and we ended up with this slightly strange but essentially effective detail where there's an air gap with insulation. The middle image is showing the arrangement around wrapping the underside of a slab with insulation, which is still in progress. But I think that the part that we were that we learned the most from was where the top of the windows and that curved facade element is happening, and we've got a wall that's running all the way up to the soffit, the structural soffit. That is fully insulated, and really the main reason for us doing that was we were concerned about the robustness of the insulation, which, as you can see in this image quite clearly, is not great when it's sitting on top of the lightweight ceiling framing. So what we ended up doing was a full upstand wall in that space with insulation plus the soffit lining. And then in the image on the right hand side, again, this is a little thing that we missed, and I think everyone on the team missed, but that column sitting right in the middle there is a structural column, and it was done very early in the project. And then when we went to put in the wrap, we realised that the column is actually sitting within a very wide wall build-up and is actually going to be outside the thermal line. So we ended up wrapping that column within the wall makeup, but I think we also did modelling with Oricon around the best way to wrap it, because it becomes quite difficult then, because it is always going to bridge now. So again, little things like that which in 2D seem fine, but then in 3D don't really work. Again, construction detailing, so facade was a big thing for us. There was a big discussion on facade during tender. Originally there was a punch window and precast facade, and it changed to a fully unitised curtain wall. This is something that I am very much in favour of. I'm sure there are others here who can speak more detailed numbers around the performance differences between the two options, but from a head contractor perspective, it's definitely an advantage for us. From a delivery perspective, and we also, in this drawing down the bottom, you can see we moved all the penetrations for the sunshades to above the air tightness and thermal lines. So in the shop drawing you can see all the little penetrations for the outriggers, and then in the image you can see them happening at the top of the facade, and they are actually all happening above the roof slab, which you can then see in the bottom image where we've got that outrigger penetrating and fixing down onto the structural slab roof. And again, we were able to avoid having any intermediate fixings all the way down the glazed facade to maintain air tightness and also avoid bridging issues. And you can also just see on this image down the bottom here the use of the thermal break material. So we didn't actually use a Passive House certified product. We just went with standard structural packers, which we then worked with Oricon to model and confirm performance. So trade packaging is actually one of the reasons that facade setup is such an advantage to contractors. So wherever you've got single trades working to provide the air tightness line, it de-risks the project. There's less intersection issues, there'll be less issues with QA, and if you've got good trades in those particular packages, then you're more likely to get good results. So wherever we didn't have the unitised curtain wall, which is with a facade contractors are more sophisticated and more experienced. They do a PMU prior to coming to site. You have, a fully tested system and then great QA, or potentially great QA. Everywhere else we used an asbestos contractor, an asbestos removal contractor, and they did all of our wall wrap, and our wall wrap was pretty much used wherever we didn't have curtain wall. As you can see in the images there are a huge variety of instances where that was happening, and I think again you can also see the complexity in the interfaces between different trades and how important it is that you get someone that tapes that really well. We also did a lot of work with them to kind of develop little techniques or little systems to ensure that in all the instances we were going to get great air tightness. So in that bottom left image, we did know that there was going to be some fairly significant penetrations that we had to make through that air tightness line due to construction sequencing. And so we just experimented with putting tape on the back of the wrap first before we fixed through, and then taping over the top, with the kind of thought that it would grab more efficiently if the sticky tape was kind of wrapping around that screw fixing. And we did find that that worked, so we used that quite a lot with just to add robustness and to ensure that we had no leakage. On de-risking delivery, we actually did a number of things which are fairly standard practice in the industry around MET commissioning. So we did a smoke test in the clerestory ceiling, which we knew we wouldn't have access to once the scaffolding came down. So as you can see in the section down the bottom, there's a big open void that at the moment in the video is fully scaffolded. In the image above, you can see what's happening. And so we did a smoke test, and we actually found that there was some leakage through the windows, through some manufacturing holes. So we were able to plug them up relatively easily and quickly, but we did find very limited issues with our wall wrap along the top, which was definitely an advantage. Also in this area, same principle, during construction we did some pressure testing, and one of the lessons that we learned in this was that lightweight ceilings flex heavily under air pressure, as you can see in the video. These are not scientifically calculated pressures, but we did just do it for peace of mind, and in the end we ripped down that ceiling and replaced it and re-braced it, just so that we could ensure the robustness of the air tightness was maintained post-occupation. De-risking delivery again, services penetrations. I won't spend too much time on this because I think everyone in this room knows all about it, but even with all of the additional QA that we did, all of the trades being on board with it, we still found that there were penetrations that were unsealed, and typically I think it's between plant rooms and risers that was where we found the most issues, and probably a combination of access and also a variety of trades working together. Unexpected side effects. So one of the interesting issues that we had post-occupation in this building was because of the very low mechanical ventilation system noise, there were problems with speech intelligibility between spaces. So when we did all of our testing pre-practical completion, all of our walls were meeting the required acoustic separation values. However, because there's so little white noise, and you can see just in the little table that I've got on the right there, the sounds that we were getting was between 25 and 30 dB as background noise, which is very low. It's around silent study room kind of level. So speech intelligibility is much higher when there's no background noise. And in the end, we were asked to install a sound masking equipment in certain areas just to boost that white noise and ensure that privacy was being maintained. And just quickly as well on costs, so I've just got a summary here of costs that we kind of put together very roughly. So I think the big ones is facade, and then the insulation and thermal break issues. Wherever possible, I would recommend that you don't use Passive House certified products because they generally come from overseas, they're more expensive, and they take much longer and have greater lead times and freight costs. So we typically, like I said before, we used standard doors rather than LaRosse. We used standard plastic packers rather than certified Passive House thermal break systems, and we also used a locally designed and developed thermally enhanced facade system. I think in general I would be saying overall maybe between 15 and 20% extra for a Passive House project, but I think you can find efficiencies through those areas as I've listed here. But there are also some difficult to quantify costs, like risk that contractors will price in that you may not even be aware of, and also additional QA. And I think that was the big thing from our perspective around the difference between a high performing and a passive house. It, to us, was really all in QA, and educating trades on the fact that it's not business as usual. So final thoughts from my perspective. So from the front end for designers and the like, I think it's really important that you communicate clearly the requirements for Passive House for that particular project. And I know that an ESD report is really important, but I think if you can provide a really simple matrix or a really simple memo that explains the Passive House requirements and how you're addressing them, that would be really helpful for contractors' pricing. And the second one is something that we talked about quite a bit in the presentation around wall detailing, and can they be modelled in 3D? Is there different ways that we can do that to show interfaces and intersections? And then for delivery and builders, it's really test early and often, which everyone knows, I think. Engage with your subcontractors and your design team and collaborate and educate, which again, I think is a really common one. Use known systems, use known tools, work with your contractors to use stuff and systems that they already are familiar with to deliver the same result, and to limit the requirement for re-education. And then a little note there around lifts and doors. If they're within your air tightness lines, they can be really difficult to address. You can't do much about them. And the final one is QA. And I guess from a personal perspective on Passive House, I think it's, having now worked on Monash, it's a fantastic way of going about providing and delivering high-performing buildings for the long term. And I definitely can see the value in it. And I like the fact that there is actually real-life modelling happening per building rather than kind of a necessarily checkbox exercise. So I definitely think, overall I'm less frightened of Passive House, and I'm definitely a proponent and a supporter of it for the future.
Thanks so much, Jack and ARM, for that wonderful overview of the Chacellery building. It really represents how iconic architecture and high-performance building design can come together. Next, we move on to the Woodside building for technology and design. This building really represents scale and a maturing of the Passive House in commercial buildings in Australia. Gillies Hall, one of my favourite buildings of all time, is very much the European model of building Passive House, whereas Woodside represents that in Australia we can use our local construction techniques and Asia's source materials to apply and achieve Passive House. I'll hand over now to Andrew Cortese to talk about how high performance design was achieved for this building.
Thank you, Rob. Hello, I'm Andrew Cortese, Grimshaw Partner and Design Director for the Woodside Building for Technology and Design, a learning facility for the faculties of Engineering and Information Technology. It embodies high-performance environmental design with the most contemporary initiatives in future-focused learning. It simultaneously defines, connects and enlivens a new campus realm, engaging students, staff and industry partners through the exhibition of its activities and the exposition of how it works as a living laboratory. To achieve realisable innovation, a coalition of guiding principles and qualities for the building was formed to describe the interrelationships between environmental performance, the learning program and user experience, and the transformative impact to the campus. An achievement-orientated design method was organised around a series of explorative and iterative processes: discover, create, deliver. This co-design approach invested the university to its stakeholders and users, the expert specialist advisors to the design consultants, and a delivery team aligned to strategic outcomes. It is with commendation to acknowledge Monash's key academic staff and management executive, the engineering of Oricon, the organisational and learning strategies of 6 Degrees, and the commitment by Linde to enable rationalised innovation within an accelerated delivery. Our response to the project brief situated interrelated principles through the themes of form, function and performance. These became the consistent objectives for evaluating the ongoing development of the design and for an overarching governance of the project. It was a principles and outcome-led design approach, and the evolution of the design held an explicit expression of those themes. For example, the instrumentality of the building related both to its requirement for curriculum evolution with transformation in teaching and learning, to its role as a place of exchange and enterprise, and to its performance as Passive House, and for a future-proof adaptability. The project principles and the environmental performance objectives were then held to support a series of design intentions related to user experience and to the values and commitments of the university. This hierarchy of principles and intentions enabled a unique and precedent-setting ambition for a learning building, not only responding to the currency of climate change, but for the delivery of equitable, interactive and inclusive learning and research environments, the promotion of a new ecosystem approach to transdisciplinary cross-collaboration facilities, buildings as ensemblic, open and relational, not singular and enclosed, and the delivery of these buildings with prudency in investment, all of which I hope can be observed in the following video. We will now go through a short summary of the building's program, spatial experience and performance strategies. Orientation is key not only to the environmental response, but also to allow the amenity that supports activation, comfort and enjoyment. With large format education buildings, we consider equally the qualities of the environment at the interface with the public realm, as well as those spaces within. A building with a north-facing orientation enjoys controllable sun to the north, but overshadowing to its south. While limiting solar impact to the building's envelope, it diminishes the opportunity to embrace the different seasonal and diurnal qualities of sunlight, wind, view and shade. The elongated building with its east-west orientation allows activities in the morning or afternoon sun, extensive views to the east or west, and the use of deep shaded facades, which can reflect bright daylight deep into the interior. The use of top light illuminates the central interior, and the roof is covered with an array of PV panels to contribute to its energy use. The building's envelope response is not defensive, but is designed to enable a variety of environments that embrace different types of uses and times of occupation, differentiated amenity and comfort qualities, and a more circadian experience. The shared student life of the campus occurs mostly in the public realm and commonly in the afternoon. The main pedestrian movements create different campus attributes. The Woodside building enjoys eastern views to the Dandenong Ranges across a new north-facing alumni green. Exhibition Walk is animated by the Design Build studios situated under the flowering ironbark canopies. College Walks finds an intersection at the building's entry where an open auditoria and industry exhibition space engages a forecourt. The building's environmental response is to enable the relationships between its internal program and its campus context, while minimising operational impact. The Woodside building in late afternoon sun, expressing its relationship to campus context, landscape and view. The early morning sun rises and illuminates the facade in a filigree of light, transparency, reflection and shadow. The ground plane glistens as it comes to life with the early morning movement of students and staff. The afternoon life of the campus is well known. The western facade overlooking the engineering precincts, shading low-angle sun while reflecting daylight back into the building. Ground level interaction occurs beneath the ironbark canopies. A transformative, future-focused learning environment prioritises the social and individual attributes of learning and research. The spatial themes are of diversity and inclusivity, immersion and interaction, adaptability and specialisation. There is a continuity and variety of intersecting open and informal learning and collaboration spaces that focus interaction throughout while giving experience to the different aspects of the campus context. Horizontal stratas of partitioned space are replaced by a diversity of intersecting volumetric space rationally organised within a modular frame. The environmental performance criteria for each space is dynamic and is related to the programmatic and functional intent together with its situation and orientation. The 24-metre wide central formal teaching and working spaces have high internal loads and no external loads. They are top lit. The 12-metre wide west-facing design build studios and collab studios have medium internal loads and medium external loads. The 6-metre wide informal collaboration spaces to the east contain the majority of the vertical circulation. They have low internal loads and medium external loads. The semi-public spaces around the entries, the forum spaces around the teaching spaces have low internal loads but high external loads, either heating or cooling. Servicing is distributed to minimise energy in moving air around the large floor plate and volumes, and stair circulation is situated to minimise reliance on lifting. The predominantly in-ground lower ground floor contains the 24 by 42 metre expert-led tiered learning space. The heavier loaded design build studios open to an eastern terrace for outdoor experiments. The expert-led space is visibly observed from a mezzanine-like ground level. Learning is on display and interactive. The space is protected from external solar loads but enjoys an abundance of daylights and views. The ground level holds the varying points of entry, north to south and east to west. Each entry corresponds to a large public space where all the learning, research and academic programs can be visually observed in interconnecting volumes. The south and western interfaces are activated by student uses opening out onto the surroundings. The entry forum with tiered seating auditoria connects the flat floor teaching above and the expert-led space below, with industry engagement and design build spaces surrounding it and the circulation immediately adjacent. It is a dynamic and interactive south-facing space that opens back onto the forecourt and looks back to the campus. Within the modular frame, the complexity of the interior volumes unfold sequentially in movement. The main south entry situates the user at this point of spatial interaction. Beneath the tiered auditoria, looking into the lifts through the informal spaces surrounding the expert-led theatre and up into the offices above, a diversity of spatial interconnectivity modelled in both sunlight and daylight and with views across, down and through. Alliance Lane bisects west to east, descending into the new alumni green. The different environmental and visual effects of the facade and roof can be observed. Level 1. The Great Terrace of Flat Floor Adaptable Teaching. The immersive learning environment has informal breakout spaces to the east and has collab studios adjacent to the west. At the top of the auditorium tiers, an informal learning space addresses the main flat floor teaching space and simultaneously looks up into the academic offices above. It is illuminated with top light. Along the east, the informal collaboration and learning spaces have interconnecting stairs with engaging views both up and down and out across the alumni green. The interior of the 24-metre wide flat floor adaptable teaching studios. They have a high level of control and are technology rich. The flat-floor teaching spaces are surrounded in formal learning spaces which are illuminated from the atria space which aligns to Alliance Lane. On levels 2 and 3, the academic research and support staff are located around two-storey atria in clusters of around 45 people. These neighbourhoods open into collaboration spaces to the east, and the CoLab teaching studios are located to the west, which can also be interchanged with workplace on the upper level. The workplace clusters beneath the top-lit atrias have an abundance of daylight and allow visual and spatial connection between the focus rooms and from one side of the building to the other. The workspace clusters have collaboration breakout spaces to the east, which overlook the scenic Dandenong Ranges. In summary of the overall design strategy, we have roof-mounted PV panels connected to the campus microgrid, skylights to illuminate the central interiors, a high-performance facade with variable amenity, a layering of the internal program giving a variety response to internal and external loads, a diversity of interconnected spatial volumes, roof water catchment, and distributed services and vertical circulation. I now hand over to Alberto, who will describe how our passive house performance was achieved.
Thanks, Andrew. So this section of the presentation focuses on the solution adopted in the facade design and the design process that allowed Grimshaw and the design team to investigate, explore, and consolidate these solutions. In order to summarize the facade design principles, the building presents an overall 50% window-to-wall ratio, which is fundamental on one side to achieve the required thermal performance of the envelope in terms of U value, and on the other side to achieve optimal level of daylight in the internal spaces. More specifically, the east-west facade managed the solar radiation through a 50% transparent and 50% solid insulated area, and with the use of external fins. The north facade is completely solid and highly insulated, and the fully glazed areas enclose the atria and main entries of the building on the south, east, and west. This layout is the result of iterative studies that were undertaken since the early stages and consideration on performances, buildability, budget, comfort, and of course architectural refinement of the envelope. And now we can see a few close-ups of the facade, starting from the unitized curtain wall with an average 50% window-to-wall ratio and the array of external fins to manage the solar radiation. This is a shot of the fully glazed south facade and roof, which allows a high-quality diffuse light into the atrium. And this is a shot that shows the contrast between the stronger texture of the charcoal grey curtain wall given by the external fins and the finer grain given by the horizontal louver colored in red gum that screen the stairs and lift cores. The facade design outcome that I just described is the result of the use of an early stage performance-based design approach. This approach started in the concept phase where given the orientation of the building with the predominant east-west elevation, it was clear that the key to reach the building performance set by Passive House was to find the best way to manage and balance daylight and thermal performance on these two elevations. In this early stage, in collaboration with Bollinger and Grohmann, we took the basic principles of solar shading design, and with the use of a parametric software, we built a script that enabled us to run a multivariable performance-based optimization analysis. The aim of the script was to find the best balance between window-to-wall ratio to achieve the target U value and the best layout and dimension of the external fins to minimize the solar radiation into the building. We use this analysis to manage the complexity of the process and find the sweet spot that optimizes the design targets. This diagram shows the result of this optimization process and acknowledges the relationship between the window-to-wall ratio, the moderate shading provided by the external array of fins and louvers, the estimated glass performance, and finally, the peak cooling load used to comply with the passive house targets. Another important outcome is that this process allowed the design team to control the transparency of the glass, future-proofing the use of a high-performance glass with high transparency and visible light transmission. This early-stage design exercise gave us the parameters that then became the backbone of the facade design, allowing a more detailed optimization process to follow. So this second step aimed to further refine the design and considered detailed thermal performance, fabrication, construction, and cost optimization. In this slide, there is a summary of the systems used as main facade types. On the right side, an early stage sketch captures the unitized curtain wall with the thermal improved glazing beads and the stainless steel bracket that connects to the external fins. On the left, the sketch of the high transparent facade that encloses the atria on east, west, and south elevation with a steel structure that support the thermally broken aluminium adapter. Both systems suit very well the modular nature of the facade that is based on a 900mm grid, and especially the unitized curtain wall frame offer great flexibility in supporting different types of shading system. A comparative thermal study undertaken in-house allowed us to provide evidence to support the use of our argon-filled double glazed unit instead of the triple glazed unit solution that was originally explored, simplifying the glass composition and reducing the cost of both glass and aluminium frame. A similar study, realized in partnership with the Prism Facade, also allowed the design team to compare the thermal performance of a typical European Schuko system with a typical Australasian thermally broken curtain wall. This comparison showed similar performances and was fundamental to reduce the cost premium on the facade in the pre-tender phase. A similar detailed thermal study was used to analyze the thermal behavior of the bracket that connects the aluminium frame to the fins. And a standard aluminium bracket resulted in exceeding the heat exchange limit defined by passive house, and an alternative solution in stainless steel had to be adopted instead. This slide summarizes the main performance of the unitized curtain wall with reference to the passive house principles. So starting with the high performance glass that consists of a double glazed unit filled with argon gas, then the spandrel panel insulated with a non-combustible mineral wool. On the right, the multiple level of weather protection provided by gaskets and silicon joints, typical of a pressure equalized unitized curtain wall. And as I briefly mentioned before, our thermal bridge-free design system that minimizes the heat transfer through the use of stainless steel brackets. Finally, great importance was given to the design of the skylights. The design process aimed to balance competing performances in terms of daylight requirements and solar radiation. On one side, the aim was to maximize the daylight requirements without occurring in glare issues, and on the other side, to minimize the solar radiation ingress to comply with the maximum cooling peak load defined by passive house. The exploration process used a daylight analysis software to compare different design options, including the first option with a vertical skylight facing south with a sawtooth roof, two vertical skylights facing south and north with the second shaded, and the last option is two horizontal skylights with the integrated shading system designed to screen the direct light and radiation and reflect diffuse light in the space underneath. And the last one was the solution that then was applied to the building. So this analysis showed how the first two options were inadequate and how the use of a screened horizontal skylight achieved a better compromise. guess that for us, the main lessons learned are that an early stage performance-based approach is fundamental to find the best balance with the competing performances, for example, daylight distribution and thermal. And from the point of view of the architect, to keep the control over the design. The second one is that the Passive House standard provides a great framework to design and manage high-performance building from design to construction. And then looking at the broader meaning of sustainability, I think that the Passive House criteria must be integrated with additional metrics that look after other important aspects of the design, such as embodied energy or social equality. And finally, the Passive House performance targets can't be reached without a close collaboration with clients, architects, consultants, and contractor. And now I hand over the presentation to Jeff, that will be talking about Oricon perspective on the design process. Thanks.
Thank you, Alberto, for that great presentation. I'm Jeff Robinson, and I had the good fortune of being Oricon's project director on the Woodside building from concept to tender, and I'm delighted to talk to you about the building engineering design for this industry-leading sustainable building. As an engineer who's worked on the design of sustainable buildings since the mid-1980s, the Woodside Building for Technology and Design was an amazing project to work on and a career highlight for me. It was great to have had the opportunity to collaborate with such a passionate and talented group of people working for a very experienced client with the highest of sustainability ambitions on a building that will allow a generation of engineers to learn what world-class sustainability looks and feels like. As Rob showed at the start of the presentation, Monash University has been on a steadfast sustainability journey for the last few years, taking the lessons learnt on previous projects and applying them to their next. Rob's ambitious brief for the Woodside building was that it should meet the certified Passive House standard, as well as delivering excellent indoor environmental quality to its occupants and achieving Monash's Eco Accord ESD requirements. To achieve the world-class building energy and comfort standard that Passive House certification confirms was not an easy endeavour, and it required Grimshaw and Oricon to work collaboratively together from first principles using an integrative design process where workshops are held at each stage of the project to allow mutual discovery of approaches and co-rationalization of designs that have multiple benefits to the project and contribute towards achieving the project ESD and other goals. Research and analysis was carried out between the workshops to gather critical information, and both Oricon and Grimshaw carried out technical analysis and modelling to test different approaches and design proposals. The translation of the integrated design into the constructed building was greatly assisted by Lend-Lease, both through early contractor involvement and through the common commitment of the architects, engineers, and contractors working together during construction to do whatever it took to achieve the Passive House certification. Our experience of using an integrative design process on the Woodside building is that it was a great way to work together to break down traditional silos and to bring the best thinking of the whole design team to overcome one of the challenges of our industry, namely how to cost-effectively deliver well-insulated, airtight buildings which are comfortable to occupy and are low energy in construction and operation. To start the process for achieving the ESD objectives for the project, we facilitated a number of co-design workshops with the design team, students, and members of the faculties of engineering and IT. We used the Lenses regenerative framework to explore with the participants what a regenerative future for Monash might look like. We explored what a successful outcome for the project might be and the alternative if the project was a failure, alas poor Ted. The conversations and exercises in these workshops generated a series of agreed guiding sustainability principles to chart the direction and priorities in the subsequent development of the building design. These guiding sustainability principles were that the Woodside building should be future-ready and adaptable, facilitate a thriving community, living within limits, facilitate continuous learning, be a well-loved building, and create a biophilic and healthy environment. We are confident that when the Woodside building is fully occupied and in use for some time, that we will see that these guiding sustainability principles will have been fully realized. The successful application of the integrative design processes can be seen throughout the building, with single pieces of construction delivering multiple benefits. The passive house principles of a high-performance thermal envelope with continuous insulation and minimal thermal bridging and an efficient mechanical ventilation system with heat recovery have been incorporated throughout. The building supports Monash's net zero energy targets by being all electric, highly energy efficient, and powered by a 273 megawatt hour roof mounted PV array, which is connected to Monash's campus microgrid. The building has been designed as a living laboratory where engineering and IT students can use the building as an intrinsic part of their pedagogy. The passive design elements and building services are all on display. The structure of the building is clearly expressed and sensors have been installed. Monash's requirement for excellent indoor environment quality have been fully realized through integrating multiple design elements, including the well-insulated airtight facades, the efficient fresh air ventilation systems, the glare-free daylighting, the well-considered acoustic design, and the extensive use of timber with its biophilic benefits. The building, with its wide stairs and comfortable and healthy environment, was extensively used by the university during the first stage of the pandemic. Some of the many examples where the Woodside building has been designed as a living lab for students and researchers are shown on this slide. A number of thermal piles were installed to be used for research and teaching about geoexchange. The piles have strain gauges and pressure sensors installed to facilitate their ongoing monitoring and research. Building services are on display throughout the building, including providing vision panels into plant rooms. The thermal piles flow and return headers are on display in the lower ground plant room, and the energy measurement system is integrated into the building management system for monitoring of experiments. The ground floor informal study space is heated and cooled using pipework embedded in the concrete, and a display window has been placed in the floor to let students see the installation. There are many other examples of systems and data which are available to the engineering and IT students for integration and experimentation, which unfortunately the time available for this presentation doesn't allow me to share with you. I'm now going to hand over to my colleague Walter, who will tell you about the high-performance building engineering strategy developed for this project. Thank you.
Thank you, Jeff. Let's dive into the building engineering strategy. We'll be talking about the strategies implemented to achieve passive house certification, such as the use of mechanical ventilation with heat recovery, constant air volume dampers for modulating the outside airflow rate, high efficiency condensing units for heating and cooling, high efficiency CO2 heat pumps for the domestic hot water generation, and solar PV systems to increase the PER generation. The HVAC plant is distributed on each floor and consists of 11 heat recovery ventilation units, ranging in air quantities from 1,500 liters per second to 3,250 liters per second, and one full outside air unit delivering an air quantity of 3,600 liters per second. The heat recovery units are located on a floor-by-floor basis, serving the northern and southern zones of the building separately. The typical zoning showed here is applied to the ground level and levels 1, 2 and 3. The outside air is distributed to the various spaces, and the heat is being recovered from these same spaces using the corridors as the return path to the mechanical plant. Supplementary cooling and heating is applied via fan coil units and assigned to the various spaces like offices, meeting rooms and collaborative spaces. The condensing units serving the fan coil units are modular variable refrigerant flow condensing units of the heat recovery type. They are located on the roof and have an installed cooling capacity of approximately 1,400 kilowatt and heating capacity of approximately 1,600 kilowatt. On lower ground level, there are large spaces on the southern side, such as the informal study highlighted in yellow and the tiered collaborative space highlighted in green. The informal study area highlighted in blue is actually located on the ground level and the plant sits right below it. Here on the right hand side you can see a photo of the informal study space. These three spaces highlighted in blue, yellow and green make use of positive displacement to condition the space in the form of floor grills or sidewall grills. The northern side of the building on this level mainly consists of a large design studios, amenities and storage spaces. The rainwater harvesting tank is located in the northwestern corner. The electrical and prototyping studios have general exhaust ventilation, and the machine studio has process exhaust systems for the spray painting booth and the welding room. Makeup air systems have been put in place to assist with the building's overall pressurization. The eastern entrance, aligned with a lion's lane, and the presentation area in the ground floor informal area makes use of underfloor heating and cooling via a heat pump delivering chilled or heating hot water to assist with the conditioning of these spaces. To meet the passive house stringent energy requirements, the fan power consumption by the mechanical ventilation units with heat recovery need to generally be below or the same as 0.45 watt per cubic meter per hour. That means the pressure drops starting from the outside air intake all the way through to the outside air supply ducting back to the return air ducting and discharge through the exhaust air louvers need to be as low as possible. This required careful consideration during the selection of the mechanical ventilation units with heat recovery. The ducting design was optimized for the smallest pressure drop, while allowing the other building services to be reticulated throughout the building. Low airflow velocities and guide vanes became a critical consideration to reduce the pressure loss across the system. The outside airflow is accurately controlled via constant air volume dampers, denoted as CAVDs. Where large quantities of outside air are delivered to a space, the dampers are motorized to modulate between minimum and maximum design values. The building management system has been set up to maintain air balancing at all times of the building operation. The fan coil units were fitted with some energy-saving initiatives, like motorized diffusers, providing variable air volume to selected spaces. These VAV diffusers have been fitted with flow meters to accurately commission the supply air flow rates through the BMS. Occupancy sensors have also been installed in various spaces to allow the fan coil units to switch off when no one is present. In large spaces, CO2 sensors have been installed to modulate the outside air requirement and subsequently reduce the fan power consumption. The condensing units play a big role in energy consumption. Specifically for a large building like this one, where internal loads can be quite high, supplementary cooling and heating will be required. So, to meet the overall energy consumption benchmarks, the condensing units selected need to operate at high efficiencies. This is a fundamental step that can't be overemphasized. The same goes for the domestic hot water. If you want to meet the energy consumption benchmarks, then a stock standard air-cooled condenser won't do the trick. In this case, the domestic hot water system utilizes a CO2 heat pump, which offers significantly higher electrical efficiencies. We've also designed the system with well-insulated water storage tanks to assist with the fast response of hot water generation and reduce the need to constantly run the heat pump. When I was preparing these slides, I kept on thinking it feels like I'm using the word high too many times, but I just can't get it out of my system. Once again, we need high-performing solar panels. The panels selected are exactly that. They offer parallel circuitry of solar panels to reduce the risk of soiling, and the system makes use of 4 inverters balanced across the entire roof layout. The PV system has an installed capacity of 230 kilowatt peak, A shading analysis was undertaken to decrease the shading losses of the system, and as you can see from this aerial photo, the western facade is at the bottom of the page. This photo was taken quite late in the day. There's a clear shadow line formed by the mechanical plant in a few locations. Then in between the skylights there's some shading in as well. That's about as bad as it gets, and the rest of the panels are fully exposed to generate renewable power. This building has been designed to be a near zero carbon building. It required collaboration between Grimshaw, Oricon and Linde to maximize the available roof space while providing safe access to all the engineering services and other components that needed maintenance and cleaning. The PV system also has the potential to provide energy back into a microgrid and share the renewable energy where it is most required. Monash University came to Oricon with a strategy stating that they are aiming to achieve net zero carbon emissions for all the energy used on their campus by 2030. Effectively, this means all the energy used will be from renewable sources. In order to achieve this, the services use electricity, which gives Monash University the ability to change over to renewable sources with relative ease. The building is fully electrified and no gas is used on site. Let's have a look at some of the key components. Typically, gas is used for generating heating hot water and domestic hot water. This building uses VRF systems for heating and CO2 heat pumps for domestic hot water. During the selection of the system, practical factors such as plant footprint, maintenance access, and the ability to effectively reject the load were considered. The VRF system provided high efficiency performance in heating mode and a modular approach which gave us the ability to maximize the available roof space for the solar PV layout. The CO2 heat pump offered unparalleled performance during low ambient temperatures, and because it uses CO2 as a refrigerant, it has a global warming potential of 1. If you're all electric, then it makes sense to aim for a reduced PER demand and an increased PER generation. Part load efficiencies are readily available for chillers and heat pumps generating heating hot water. However, this is not the case for variable refrigerant flow systems. We approached the Passive House Institute, who were acting as the certifying body for this building, and with our input they generated a VRF evaluation tool to assist us to determine the electrical demand of the VRF system. The tool takes into consideration the indoor air temperature, which has the boundary conditions of 20 degrees Celsius for heating and 25 degrees Celsius for cooling. The outdoor air temperature boundary conditions is based on Melbourne's weather data file. To add further complexity, the evaluated system needs to take into account the combination ratio, which gives the VRF plant the ability to add additional indoor units to each set of condensing units. Generally speaking, the system has made allowance for an additional 20% of heating and cooling load to meet the building's future needs. Based on the selection received from the suppliers, the capacity tables in both heating and cooling mode were used to obtain the input power and the associated available heating and cooling capacities. These design values and test points below and above them were used to determine the coefficient of performance in heating mode and the energy efficiency ratio in cooling mode. The result is a neat little linear graph telling us that in heating mode the average weighted COP at approximately 10 degrees Celsius is 2.7 and the average weighted EER is 3.4 at approximately 23 degrees Celsius. These values were then populated into the PHPP to accurately determine the PER demand. To further limit the PER demand, the domestic hot water generation system was designed to reduce system losses. This means that it's well insulated all the way through up to the point of use. The building has two 15 kilowatt CO2 heat pumps, which have been strategically placed as close as possible to the riser, limiting the vertical runs of the circulation piping. The same riser path is also used to limit the length of accumulated single pipe runs, and lastly, the maximum number of tapping points are used per riser. All these seemingly straightforward design decisions have a significant impact on the domestic hot water system's PER demand. It's worth noting that the CO2 heat pumps provide excellent energy efficiency. In this case, it has a seasonal performance factor of 4. To keep track of all the moving parts during the design phase, we used Design pH and the PHPP. A key observation was that Melbourne has a relatively benign climate, which reiterates the need to review part load operating conditions of the heating and cooling plant. The approach was mainly to capture services in the PHPP and document the thermal properties of the building materials in Design PH by assigning them to the actual modeled components. As the design progressed, we did sensitivity analysis on items like the skylights and checked the resulting impact on the services. We also undertook thermal bridge modeling of various junctions and provided the calculations as part of the certification process. This involved a rigorous step-by-step approach, which at the end turned into quite a streamlined approach, and in hindsight, we could have done this sooner. We continuously tracked the PHPP against the design. It allowed the team to collaborate and test fit the best solutions. In terms of hierarchy, we locked down the building geometry and orientation first. The treated floor area and thermal envelopes properties were next on the list. After a baseline was established for the passive measures, we moved into the services and evaluated how best to operate the ventilation system and iteratively work towards finalizing the PER demand. The intent was always to balance the heat loads and heat losses. Finally, after evaluating the various factors and capturing the as-built information into the PHPP and Design PH, the results came together. As you can see, we fulfilled all the energy criteria, but it's worth noting that the solar PV generation allowed us to increase our PER demand. Even so, we're right on the border of the allowable PER demand, which points out that the electrical loads from the mechanical ventilation units of heat recovery, the VRF plant, the domestic hot water plant, and equipment loads need to be kept to a minimum if you want to achieve the stringent energy benchmarks. So what are the key challenges we experienced and what key lessons did we learn? A holistic approach is necessary. Mechanical ventilation units with heat recovery, constant air volume dampers, and a well-designed air distribution system is required to meet the specific fan power requirements. The heating and cooling strategy needs to take into account part load conditions during the selection process. The domestic hot water plant has a significant effect on the overall PER demand and should not be underestimated. The detailed evaluation of the thermal bridges for such a large building should be done as soon as possible. The main takeaway from my perspective is that for large buildings, services have a significant impact. I'll now hand you over to Ben to tell you more about the construction of the building.
Thanks, Walter, and good afternoon, everyone. So from a construction perspective, what we've found to be enormously important was ensuring that we had a consistent approach across the whole project with all project teams in terms of everyone knowing what part they played in getting to a point where we would achieve Passive House certification for the project. So we developed a Passive House detailing manual, and you've got some images at the bottom of the screen there. What we did to pull this together was we went through all of the design documents across the project, and anything that was relevant to Passive House, we consolidated all of those and incorporated them into this manual. We then went through on a drawing by drawing basis and marked them up, and you can see some little text boxes in there where we would identify what has to happen at each of these junctions, and referring back to whatever the relevant detail or section was. When you go to that detail or section, we then provided a narrative around the step-by-step process that was needed to ensure that it was built in the correct sequence, that the products, materials were all clearly identified, and importantly, which trades were responsible for each aspect of that process. So it really was a step-by-step guide for how to achieve those Passive House details. Also within the detailing manual, we had clear hold points where works could not proceed beyond a specific point without first being inspected and ticked off by our QA person on site. And this took place for every single detail that was relevant to Passive House. So it predominantly centered around facade and the building envelope and the roof. They were the main contributors to the success or failure of Passive House. This pack really provided us with a lot of certainty from the outset that our teams understood what was needed, understood each detail intimately, and what was needed to get to that Passive House certification point. So another really important innovation for us was getting early engagement with a reputable facade contractor, and that was really needed to ensure that we could identify readily available extrusions and gaskets that could be used or modified to ultimately, achieve the Passive House requirements on the project. So the facade contractor was probably the first trade that we procured on the project, and that was very strategic in terms of the approach that I've just outlined. So once we had engaged a facade specialist and identified which facade suites we were going to be used, we undertook extensive off-site prototype testing of all junctions across the project. We built one-to-one models and undertook that testing, and that was in collaboration with an airtightness specialist consultant who we engaged to provide really early design advice related to the air barrier line, and to provide early identification of any points of weakness that would need designing out. And you can see some images there off to the right, those 4 images stacked on top of each other. That's where we built these one-to-one prototypes and then undertook the pressure testing of those. Once we were satisfied that they were meeting the performance criteria and performing as needed, we then went into mass production of those relevant sections of the facade, delivered them to site, installed them, and as quickly as possible following installation, we would start doing on-site air leakage testing. And you can see that by the largest image there, where with our air tightness specialist, we'd cordon off a room and do an air pressure test. In that particular instance there, we can see that there was a leak, some air leakage coming out from just under those louvers there. And I think that particular one was in relation to a flashing that had some gaps between it and the substructure. So enormously beneficial and useful. We were able to identify very early in the piece any areas of weakness and be able to address those. So once the facade or the building envelope started coming together, there were regular site inspections and tests that were ongoing for the duration of the project. And that was done hand in hand with our airtightness specialist. So during the building and documentation process, having that suite of documents that clearly identifies the airline barrier and references all associated details was critical for us. We were able to, and you can see some images there where we knew that there were details that would be hard to get to once they were built in. We were able to get cameras to inspect the cavities of walls and identify any sections where seals or joints might be not have come together as required, and we'd be able to rectify those earlier. So this was made a lot easier by creating another schedule. It was almost like a secondary door schedule, really, where we identified all apertures and doors that passed through the airline barrier, and ensured that we had appropriate fittings that would provide the relevant air tightness for that. An example of that might have been a door that passed through, or a window that passed through, where we had to get a very specific airtight door seal that was only available through Germany. We were able to identify that early in the piece before any testing was undertaken. When those tests were undertaken, it was very pleasing that those seals performed as required. Had they just been documented as business as usual, as an off-the-shelf one that's readily available here in Australia, might have been a different outcome and resulted in us needing to do some scrambling at the back end. Fortunately, that wasn't the case. Look, really important, going back to that consistent approach across the whole site, where everyone understands the level of rigour that's going to be required and what their responsibilities are. That induction across the site is enormously important, and really something that I know I keep going over, but that's what helps gets you that end outcome that you're all after. Another key point for us is having an on-site air tightness champion that liaises with all of the trades, the consultants, and really does carry out those daily site checks and inspections, and does this sort of thing here with the the camera, doing those inspections, recording the evidence, and moving on to the next detail before you start commissioning and testing the building. So to validate the performance of the building, we would generate these incomplete works lists where we knew that there were issues that had been identified through our QA hold point process. And that included comments from our air tightness specialist. They would get then issued to our teams internally, and we would have a session as a team working through what needed to be done for each of the problem areas. Our foremen and engineers would then take that back through our subcontractors on site, and there'd be a once a week meeting that we'd hold with them where this would all get tabled. They'd either be closed out, in which case it'd come back for us to go and recheck, or they were identified as not being closed out. If there were any items that were lingering a little longer than they needed to, we'd escalate those pretty quickly through the site leadership team, and they could address it with the subbies at a principal's level. So this slide here just shows the controls that we had in place to manage that whole QA process. So off to the right of the screen there, you can see we'd take floor plans and elevations of the building, and as we would do the testing, we'd identify any weak points or areas that weren't performing as needed to. We'd provide a little description around what the issue was and what needed to be done. That all then got captured in our overall spreadsheet, which is off to the left of the screen there, where we would identify the item location, the photograph number, what the size of the penetration or issue was, what the status of it was in terms of whether or not it had been inspected by Lend-Lease or just identified by the air tightness specialist, whether photos were taken of the issue, had it been rectified and checked and closed out. And this was the tool that we used at our weekly meetings with the subcontractors to be able to track and close out the overall progress of the issues that were being experienced. In terms of the costs associated with delivering a passive house building, our experience on the Monash Woodside project was that they were really pretty minimal in the scheme of things. Compared to what would be a business as usual scenario, I think the premium that was paid for Woodside was somewhere in the order of 2.5% of the design and construction costs. Look, that will vary depending on the complexities and other design aspects of a project. So things like, the configuration of a building, how repetitious the facade design is, whether or not there are, different facade element or material types. All of that's going to contribute to the passive house associated costs. So areas where we did spend additional costs would have been on the substructure, so there was additional insulation that was required through there. On the facade and the roof, so that whole building envelope, it's really looking at improving the U values, reducing the extent of thermal bridges, and getting the solar heat gains managed, whether that's through vertical and horizontal sunshades or treating the glass. Air tightness is another key area. A lot of work went into that, and I think you've probably got a flavour of that through this talk that we're doing. Looking at apertures and doors related to thermal and or air tightness issues. Services really need to look at the heat exchange and efficiency requirements. And there is that extra resource that really needs to be allocated to ensure that those daily QA inspections and monitoring are managed really at that level of minutiae detail that's required to deliver Passive House. So look, the other thing I'd say is that the cost premium, it is likely to reduce over time as more and more projects are delivered and the industry consultants become more in tune with and get more experience with delivering these Passive House buildings. Challenges and lessons learnt. I think probably our biggest challenge on Woodside building was its incredibly tight program. We had 16 months to complete design, do all the prototyping, testing, and construct the entire project. There were multiple critical paths in the program that were on-site and off-site, and that was probably the biggest hurdle that we had to overcome. And for some of the reasons given earlier in my talk, engaging a facade contractor early in the piece, having a clear strategy around how you're going to do all of that is critical to the success of being able to deliver a Passive House building that has a very tight program associated with it. I keep going on over it, but the ensuring that the project team are provided with an induction on the principles and the requirements of Passive House, and everyone's clear in terms of what their roles and responsibilities are in achieving the outcomes. Our Passive House champion for the project, we put her on a 10-day Passive House tradesperson course and got certification. She got certification at the end of that. That was really important for helping us navigate through different stages of the project and really gave us that level of confidence that while it wasn't left up to any one individual, it was certainly there was certainly someone within the team who had that next level of understanding around Passive House principles. Very important to aim for early engagement with the design team to review the level of resolution of design and the all-important Passive House planning package document and its level of completeness. And another key one for us, engaging an independent peer review of the Passive House during the tender phase. That really helped us assist with the review of thermal bridging checks, the extent of insulation that was going to be needed, everything that was fundamental to the success of delivering a Passive House building. We really delved into that during the tender period and made sure that we understood that, such that we were able to give a commitment to Monash as part of our tender offering that we would deliver a Passive House building. So look, that really wraps up my section. From a construction perspective, we'll now look to wrap up our overall section here on the Monash Woodside building and hand it back to some of the other team members just to conclude.
At Grimshaw, we have committed to the goal of delivering net zero carbon ready buildings by 2025 and socially and environmentally regenerative buildings by 2030. With respect to design services, that commitment is upon us at this very moment, and the criticality to address climate change is immediate and substantive. We emerge from the impacts of COVID with the possibility of a more personal understanding of the potential for alignment and coherence amongst architects, engineers, contractors in their shared responsibility to enable our clients and their investment partners to lead, knowing that there is a resolute commitment to achieve these goals. I would perhaps go further in noting that out of these times, perhaps we feel an overwhelming optimism to embrace the immediacy of that mission and almost a frustration when doubt or risk is presented. Monash's Woodside building embraced the challenge to achieve Passive House in 2016. Passive House is one of the most significant pathways to achieve net zero carbon. The architectural design of the building, its learning and research program, its cost and its delivery program were not impacted by that commitment. The building demonstrates not only the ability for a 2/3 reduction in operational energy, but a fundamental shift in the ethics of design, where architecture is foremost in service of enabling these goals as the imperative above all, and that such utility provides the fertile ground for the expression of meaning, beauty, and relevance.
The Woodside building demonstrates that with the right level of rigour, attention to detail, and a collaborative approach, complex, large-scale new buildings can achieve the Passive House certification, with long-lasting benefits to the owners, occupiers, and the environment. Lend-Lease look forward to continuing to work with clients and their teams to create value through places where communities thrive, such as the Woodside Building for Technology and Design.
Monash Woodside has been a really great project to be part of. The experience gained by the team to successfully achieve Passive House certification will be applied by all involved to meet the critical design and construction challenge of our time: how to deliver the net zero carbon buildings that commercial, educational, and institutional building owners are looking for to address the climate emergency we are currently facing. We hope that the Passive House certification of the Woodside Building for Technology and Design inspires the wider industry to demand well-insulated, airtight and all-electric buildings, confident in the knowledge that they will be delivered for little or no additional cost premium.
For large buildings, this project has made it abundantly clear that engineering services play a significant role in achieving the stringent energy consumption benchmarks required for Passive House certification. We hope to further evaluate and monitor the building's energy consumption to compare the actual energy used against the predicted consumption in the PHPP. This will further improve our understanding of the practical implementation of Passive House principles, which will help us to close the gap between design intent and reality, and we look forward to share our findings with the design community.
Hello everyone, it is such a great pleasure to be granted the final word on this presentation. My name is Dragoș Arnautu and I consulted and certified this project on behalf of the Passive House Institute in Germany. The Woodside Building for Technology and Design is currently the largest Passive House certified project in the Southern Hemisphere and surely one of the largest certified educational buildings in the world. It is a landmark representing the latest thinking in tertiary education and leading energy-efficient building design in Australia. Together with the Gillies Hall student dormitory, the Monash University has demonstrated everyone that beautiful architecture and energy efficiency go along quite well, and most importantly that yes, it is possible. I would like to salute their engagement and to assure them that we, the Passive House Institute, are here to support such sustainability-driven actions. It has been a real pleasure to be part of this team, and with this opportunity I would like to thank everyone involved for making this project happen and for making this project a certified Passive House. A special thank you from my side goes to Rob Brimblecombe and Johanna Trickett, without whom this project would have not been possible. Thank you very much.